Hello everyone. So in the previous class we discussed about polynomials, degree of a polynomial and polynomial rings, and we note that the collection of all polynomials over R forms a ring, and in fact if R is the integral domain, then R of X, which is collection of all polynomials over R, is also an integral domain. Now let's continue the discussion. Now, today we are going to discuss some examples of ideals of Z of X. We know that Z of X is a commutative ring with identity. Since Z is an integral domain, so is Z of X. Now, let us consider the ideal generated by X. In fact, this ideal is a prime ideal but not a maximal ideal of Z of X. Let's see why it is. The collection, the ideal generated by X is nothing but collection of all elements of the form X into f of X, where f of X is in Z of X. That means you are multiplying every polynomial of f of X by X. So you're going to get polynomials whose coefficients are integers, but the constant term is 0. So we are having collection of all those polynomials of Z of X whose constant term is 0. That is our ideal generated by X. Now let us consider a substitution map phi from Z of X to Z defined by phi of f of X equal to f of 0 for all f of X belongs to Z of X. In fact, this mapping is homomorphism because it satisfies both the conditions of ring homomorphism. And further, we knew that Z is contained in Z of X. So every integer which is present in Z of X is treated as a constant polynomial. Therefore, suppose if n is any integer, then it will be assumed as a constant polynomial in Z of X, say f of X. Then phi of f of X will be equal to n. Therefore, this mapping is onto. Hence, this mapping is onto ring homomorphism. And further, kernel of this mapping is given by collection of all domain elements whose image under the mapping phi is 0 element of codomain. But we knew that phi of f of X is f of 0. Therefore, we are getting polynomials of Z of X whose constant term is 0. So, in fact, this is nothing but our ideal set, that is ideal generated by X. Thus, all the conditions of fundamental theorem of homomorphism of rings are satisfied. Hence, by fundamental theorem, domain divided by kernel is isomorphic to codomain. But we knew that Z is an integral domain, and there is a result which says an ideal P of a ring R is said to be prime ideal if and only if R by P is an integral domain. Since Z is an integral domain, Z of X by principal ideal X is also an integral domain. Hence, this ideal generated by X is a prime ideal of Z of X. And further, there is a result which says that if M is a maximal ideal of R, then R by M is a field. Because of that result, since Z is not a field, this ideal, principal ideal X, is not a maximal ideal of Z of X. Now let's move on to another example. Consider the ideal generated by 2x, and we'll show that this ideal is a maximal ideal of Z of X. The ideal generated by 2x consists of elements of the form 2 into f of x plus x into g of x, where, because we know that the ideal generated by 2x is nothing but the sum of ideal generated by 2 and ideal generated by x. Any element which is present in 2 must be a multiple of 2. So 2 into f of x, where f of x is a polynomial in Z of x, and the ideal elements present in ideal x, they generated by x, is of the form x into g of x. So combination of this will be again a polynomial, let's say some h of x, which is also polynomial in Z of x. But only thing here, since you are multiplying this polynomial by 2, your constant term will be a multiple of 2. And when you multiply this polynomial from x, you will not be having any constant term. So when you add these two, you will get a polynomial whose constant term is a multiple of 2. So that means h of 0, which is a constant term of this polynomial, must be a multiple of 2. Now we knew that there is a canonical homomorphism eta from z to z by 2z. This mapping is onto ring homomorphism. And just now we proved that the mapping from z of x to z, say phi, that is also onto ring homomorphism. Therefore, their composition psi is also onto ring homomorphism. Further, the kernel of this psi is given by collection of all domain elements, because psi is a mapping from z of x to z by 2z. Image of the polynomial of z of x must be equal to 0 element of z by 2z, and 0 element of z by 2z is 0 plus 2z. But we know that, see, our eta, which is onto ring homomorphism, and the kernel of this mapping eta is denoted by eta inverse of 0, which is nothing but 2z. So phi inverse of eta inverse of 0 is 0 plus 2z, and in fact phi inverse of 2z equal to 0 plus 2z. That means the phi, which is a mapping from z of x to z, where you are saying that the constant term f of 0 of the polynomial f of x must be an element in 2z, because we knew that phi inverse of 2z, right, is nothing but f of 0 plus 2z, and f of 0 plus 2z is 2z, and it is of the form a plus h equal to h. That implies that a belongs to h, therefore f of 0 belongs to 2z. Now we are having a collection of all polynomials of z of x where the constant term is in 2z. In fact, this is nothing but the set, the ideal generated by 2x. Now all the required conditions of fundamental theorem of homomorphism of rings are satisfied. Therefore, by fundamental theorem, domain z of x divided by kernel is isomorphic to codomain. But we knew that z by 2z is isomorphic to z2, and z2 is a field. Hence, z of x by principal ideal 2x is also a field. And by the earlier result, any ideal is maximal provided this set is a field. So since this is a field, this set is maximal ideal of z of x. Now we'll consider another example, and we'll show that the ideal generated by 2x is not a principal ideal of z of x. Contrary to this, suppose the ideal 2x is a principal ideal of z of x. That is, it is generated by some polynomial of z of x. We knew that the ideal 2x, the ideal generated by 2x, consists of 2. So, but the ideal generated by 2x is equal to ideal generated by f of x. Therefore, 2 must be in this. But every element of this set must be a multiple of f of x. Therefore, 2 will be equal to f of x into g of x, where g of x is any polynomial in z of x. Now, we'll equate the degree of these two. Degree of 2 is a constant term, therefore degree of 2 will be 0, equal to degree of f of x into g of x. But degree of f of x into g of x will be degree of f of x plus degree of g of x. Since degree is a non-negative integer, degree of f of x and degree of g of x both must be greater than or equal to 0. But we are saying that sum of these two non-negative numbers must be equal to 0, implies that degree of f of x and degree of g of x must be 0. If the degree of f of x and degree of g of x is 0, we are having f of x and g of x as polynomials which are constant in nature. So f of x and g of x are nothing but constant polynomials, therefore they belongs to z. Because in z of x, all the coefficients including constant comes from z. Since f of x and g of x are constant, it belongs to z. But we knew that our f of x into g of x must be equal to 2. So the possibility for values of f of x and g of x will be, suppose if f of x is plus or minus 1, then g of x will be plus or minus 2. If g of x is plus or minus 1, then f of x will be plus or minus 2. So that their product will be always equal to 2. That means your f of x and g of x can take the value either plus or minus 1 or plus or minus 2. For the time being, suppose if f of x is plus or minus 1, then we'll see what happens. Suppose f of x is plus or minus 1, then the ideal generated by f of x is nothing but simply ideal generated by 1 or minus 1. We knew that the ideal generated by 1 is nothing but the given ring. Similarly, the ideal generated by minus 1 is also the given ring. Therefore, the ideal generated by f of x is simply z of x. But this is contradiction, as the ideal generated by 2x is a proper ideal of z of x. Therefore, we left out with other choice. Let's assume that f of x is equal to plus or minus 2, and we'll see what happens. Suppose f of x equal to plus or minus 2, then the ideal generated by f of x is either ideal generated by 2 or ideal generated by minus 2. For the time being, let's say it is ideal generated by 2. And we knew that x is also a polynomial present in this. But we knew that the ideal generated by 2 must contain elements of the form 2 into a polynomial. So your x will be of the form 2 into some h of x, where h of x is a polynomial in z of x. This is never true, as the h of x whose coefficients are coming from integer set. For any of the integer, we are not going to get 2 into some polynomial as x. It is possible only if h of x is half into x, and half is not an integer, so which is impossible. That's why f of x can never take the value plus or minus 1 or plus or minus 2, which is a contradiction. Hence, our assumption is wrong, that the ideal generated by 2x is a principal ideal. Therefore, the ideal generated by 2x is not a principal ideal of z of x. Now, I had given an exercise. You go through that and write it as an assignment. I had given exercise 1 and exercise 2. You do it and you write it in a book and keep it for the evaluation. Now, let's move on to next, factorization. Suppose if R is an integral domain and if A and B are two elements of R with A being a non-zero, then we say A divides B, provided if there exists element C in R such that B can be written as multiple of A, that is B equal to A into C. Then we say A divides B. In other way, you can say B is a multiple of A. Now, see, if A is any element of R, then A divides A as well as U divides A, where U is any unit of R. What is the reason? Because A can be written as A into 1. This implies that A divides A. And further, since U is a unit, we knew that A can be written as A into 1. And A into 1, which is clearly A into U inverse, where U inverse is the multiplicative inverse of U. And since this is an integral domain, I can take it outside U into any other. Now this is of this form. Therefore, U divides A. I had given one simple exercise. Show that this divisibility is reflexive and transitive, but need not be a symmetric relation. Now let's move on to next definition. When will you say two numbers are associates, two elements are associates of each other? We say A and B are associates provided A divides B and B divides A. Now, to supplement this, we are, in addition to this definition, we are having one more proposition. We can use this one also to verify, to check whether the given numbers are associates or not. Suppose A and B are any two non-zero elements of R, then A and B are associates if and only if A can be written as U into B for some unit U of R. That means one element can be written as multiple of another element. Now, suppose A and B are associates. Then we knew that by the definition of associates, A divides B and B divides A. A divides B by the divisibility definition. This can be written as A divides B, can be written as B equal to some C into A. Similarly, B divides A means A can be written as B into D, where C and D are coming from R. Now substitute A in B so that your B will be equal to C into A, where A is BD. Now after rearranging, you can write CD into B. By cancellation law, this becomes 1 equal to CD. So we are having product of C and D is equal to 1. Therefore, C and D are multiplicative inverses of each other. That means C and D are units. So let's say D is equal to some U. Then this will be of the form A equal to U into B, where U is a unit in R. That is the required answer. Now let's prove the converse. Suppose A equal to U into B for some unit U in R. Now A equal to U into B, which is of this form, by this we can straight away say that B divides A. Since U is a unit, multiplicative inverse of U exists. That means B can be written as U inverse into A, which implies, again from this result, that A divides B. So we have proved A divides B as well as B divides A. Hence, this implies that A and B are associate. So I had given one simple example on Z. Phi and minus phi are associates of each other in Z. The next example is, suppose the given ring is Z of I, the Gaussian integers, set of Gaussian integers. We knew that units of Z of I are plus or minus 1 and plus or minus I. Now, is 1 plus I and 1 minus I are associates in R or not? Yes, they are associates, because 1 plus I into minus I gives you 1 minus I. So we have written one element as multiple of another element multiplied by a unit element. So this is of the form A equal to B into U. By previous proposition, we can say that 1 plus I and 1 minus I are associates. Or the other way we can prove this one. Suppose we had given another example for this. 2 plus I and 2 minus I. Divide these two. By multiplying by the conjugate of the denominator, you will get this one. This is not a unit. Hence, by the previous result, that is, a number A and B are said to be associates if A can be written as B into U, where U is a unit. This is of not that form. Hence, 2 plus I and 2 minus I are not associates in R. Now we will define one more concept. Suppose A and B are any two numbers, elements from R, and D is any non-zero element of R, then D is called as GCD of A and B, provided D is a common divisor of A and B, and further, if D dash is any other common divisor of A and B, then D dash must divide the greatest common divisor. Now the question arises, for any two given elements, GCD exists or not? So we'll give an example for that for any two given number, GCD may not exist in general. Consider a ring Z of root minus phi, which consists of elements of the form A plus B root minus phi, where A and B are coming from Z. Clearly, this ring is a subring of complex number set, and further, your Z of root minus phi is an integral domain, which contains elements of integers. And in fact, the field of quotients of this ring is Q of root minus phi. Now let us define a mapping n from Z of root minus phi to Z by n of A plus B root minus phi is equal to A square plus 5B square. That means the image of this element is an integer. But we can write this one as A plus B root minus phi into A minus B root minus phi. And you should note that for any integer values of A and B, A square plus 5B square can never be negative because it is square. Therefore, n of A plus B root minus phi is always greater than or equal to 0. And further, this will be equal to 0 provided A plus B root minus phi is 0, which implies that A is 0 and B is 0. Now let's see some result on this. Suppose a plus b root minus 5 and c plus d root minus 5 are any two elements of z of root minus 5, then n of product of these two will be, multiply these two, then we'll get this one. Then by this result, this term square plus 5 times this term square. On expansion of this, we'll get this. Now consider n of a plus b root minus 5 and n of c plus d root minus 5 separately. By this is a square plus 5b square. This is c square plus 5d square. Product of these two gives you this. So from these two, I can say that these two are equal to each other. In general, I can say that n of alpha beta is equal to n of alpha into n of beta for all alpha beta belongs to z of root minus 5. This is one result which we got. Now, let's proceed for another result. Suppose b divides a in z of root minus 5. Then by divisibility definition, I can write a as a multiple of b. That is a equal to bc for some c in z of root minus 5. Now, n of a, which is equal to, as b divides a can be written as bc. So n of bc. But by earlier result, n of alpha beta equal to n of alpha into n of beta. By that, n of b into n of c. But this is of the form a equal to bc, which implies b divides a. By that result, I can say that n of b divides n of a as well as n of c divides n of a. And we should note that image of a, b, c are all present in z. Therefore, n of a, n of c, n of b, their result must be in z. So, we are getting if b divides a in z of root minus 5, then corresponding images n of b divides n of a in z. Now, let's see what are units of z of root minus 5. Suppose alpha is a unit in z of root minus 5. Then obviously alpha will have a multiplicative inverse so that their product alpha into beta equal to 1, where beta is the multiplicative inverse of alpha. Now, what is your n of 1? N of 1 will be equal to n of alpha beta. But n of alpha beta is n of alpha into n of beta. And since we know that n of a plus b root minus 5 is a square plus 5b square, our n of 1 will be simply 1 square plus 5 into 0 square. So your n of plus or minus 1 is 1. So n of 1 is equal to 1. Therefore, 1 is equal to n of alpha into n of beta. And we should note that n of alpha and n of beta are greater than or equal to 0. They are always non-negative. Product of these two numbers must be equal to 1, means either n of alpha is equal to 1 or n of beta equal to 1. This, and see, can n of beta and n of alpha take other than 1? No, that is not possible. Product of these two must be equal to 1, and these two are integer values. Product of these two will be equal to 1 provided both of them are 1. So your n of alpha is 1. And now the question is, so alpha, which is an element in z of root minus 5, every element of this will be of the form a plus b root minus 5. Let's assume alpha is this. Then n of alpha is equal to 1 implies alpha, which is this, by the definition of n of a plus b root minus 5, a is a square plus 5b square, which is equal to 1. This is equal to 1. It is possible only if a is plus or minus 1 and b is 0, as a and b are integers. Hence, we are having alpha, which is equal to plus or minus 1. So, alpha is a unit in z of root minus 5. Therefore, units of z of root minus 5 is plus 1 and minus 1. Now, we'll come to the actual result. Suppose alpha, which is 2 into 1 plus root minus 5, and beta, which is 6, which can also be expressed like 1 plus root minus 5 into 1 minus root 5 minus 5, have no GCD in z of root minus 5. Contrary to this, let us assume D is the GCD of alpha and beta. That means D divides alpha and D divides beta in z of root minus 5. And by this result, if B divides A in z of root minus 5, then their image n of B divides n of A in z. By that result, n of D divides n of alpha and n of D divides n of beta in z. But what is our n of alpha? N of alpha is n of this. Then this is of the form alpha into beta. So I can write n of 2 into n of 1 plus root minus 5. And by this definition, n of a plus b root minus 5 is a square plus 5b square. By that I can write this one as 2 square plus 0 square. So 2 square is 4. Then n of 1 plus root minus 5 is 1 square plus 5 into 1 square, which is again 6. So 4 into 6 gives you 24. And n of beta is n of this. And this is simply 6 square, which is 36. And we should note that our n of d divides both n of alpha and n of beta. Therefore, it's a common divisor. So what are common divisors of 24 and 36? 1 can divide both, 2 can divide both, 3, 4, 6 and 12. These are the possible values of n of d. Now we should note that d is the GCD. D is the GCD of alpha and beta. Now what is your alpha? Alpha is 2 into this plus beta is this. Here 1 plus root minus 5 divides both of them. So d dash equal to 1 plus root minus 5 divides both alpha and beta. Hence, we know that by the definition of GCD, any common divisor must divide the GCD also. So d dash must divide d. So by this result, if b divides a in z of root minus 5, n of b divides n of a in z. By that result, n of d dash divides n of d in z. But what is your n of d dash? Your n of d dash is n of this, which is 6. So 6 must divide n of d. And further, we should note that our alpha and beta both are divisible by 2. So 2 divides alpha as well as 2 divides beta, which implies that n of 2, which is 4, must divide n of d because of this result. So 4 divides n of d as well as 6 divides n of d. So both of these two numbers must divide n of d. And we are having possibility for n of d is 1, 2, 3, 4, 6 or 12. If you take any of these values 1, 2, 3, 4, 6, then 6 divides n of d and 4 divides n of d. Both of them may not be possible. So that's why we left out with the option that n of d will be equal to 12. This implies n of d is equal to 12. But d is an element in z of root minus 5. And any element in z of root minus 5 must be of the form a plus b root minus 5. So suppose d is equal to a plus b root minus 5. Then n of d is n of this, which is a square plus 5b square. And we know that n of d is 12. Therefore, a square plus 5b square equal to 12. Now the question is there any integer solution exists for this equation? No, there is no integer solution for solution for this equation. For any of a and b, which is integer, will give you 12. That means this has no solution in Z. Therefore, n of d can never be equal to 12. That means our assumption is wrong. What was our assumption? D is the GCD of alpha and beta. So there is no such GCD exists. Hence, we have proved that GCD of any two numbers need not exist in general. Thank you.